Thank you for coming to our fourth seminar in the fourth season. So hope you have been enjoying your fall semester. We're deeply into the fall semester, and I suppose people are very busy now, but thank you for being here. Today, we're going to have Professor Vagelis Papalexakis to share with us his recent research. So before we get started, let me quickly talk about some logistics, how we are going to run the seminars, right? Most of you are not new to the seminars, but for those who are new to this virtual seminar format, this is how we're going to do it. So when the speaker starts, after the speaker starts, you could be having some questions. You have several options to ask your questions. The first is that Professor Papalexakis told me that his talk is organized section by section. So during the sections, there will be some small breaks. So he will stop and ask if you have questions. So then you could unmute yourself and ask questions during the breaks. Or if you fear that you would forget the questions because you could be coming up with questions on the fly, you could just send out your questions through the chat box. So the organizers would be monitoring the chat box and try to forward your questions either in the small breaks or in the end of the talk. And also in the end of the talk, we will be having around 10 minutes of a Q&A session. So you could also ask your questions and discuss with the speaker. Okay, so that's some logistics issues. Now, please allow me to introduce Professor Papalexakis a little bit. So Vagelis Papalexakis is an assistant professor of the Computer Science and Engineering Department at University of California, Riverside. He received his PhD degree from the School of Computer Science at Carnegie Mellon University. Prior to CMU, he obtained his diploma and his master's degree in the electronic and the computer engineering at the Technical University of Crete, Hania, in Greece. So I think Crete is the place where Vagelis started his signal processing research and published his first paper in transactions signal processing, right, if I'm correct. That's right. The K-means and the co-clustering paper. And CMU, in CMU, his research is more on the data mining side, but it still has a strong flavor of signal processing theory and the method. In particular, tensor factorization algorithms for very large scale real-life data. Broadly, his research interests span the fields of data science, machine learning, artificial intelligence, and signal processing. His research involves designing interpretable models and scalable algorithms for extracting knowledge from large multi-aspect data sets with a specific emphasis on tensor factorization models and applying those algorithms to various real-world problems, including detection of misinformation on the web, explainable AI, and gravitational wave detection. His work has appeared in top-tier conferences and journals and has attracted a number of distinctions. Notably, he was recognized as a Best Student Paper Award at PAKTD 2014 and SDM 2016. Both are major data mining conferences, very competitive. He was a finalist for the Microsoft PhD Fellowship and the Facebook PhD Fellowship. He has also a lot of experience in industrial research, for example, with Microsoft research in Silicon Valley and Google research in mostly through internship, summer internship during the CMU years. He has been named as one of the 2016 KDD Rising Stars by Microsoft Academic Search, and his PhD dissertation received the 2017 SIG KDD Doctoral Dissertation Award. So without further ado, let's welcome our speaker, Professor Papalexakis, to share with us his recent research.
Thank you so much, Xiao, for the very, very kind introduction and for having me here. I'm really, really happy to be among the great roster of speakers. And I've been called by my ECE colleague, Ertem Tunsel, a double agent in the CS department. So kind of like this is me presenting my signal processor double agent work in the CS department with respect to tensor decompositions for graph mining and beyond. And so this is the menu for today. This is the road trip. First, we're going to introduce tensors and graph mining and as a nice application of them. Then we're going to continue into sort of time evolving issues and concept drift, some recent result that we have put out. And then comes the beyond, which is sort of adversarial machine learning and how tensors can help in such scenarios. And then I'm going to conclude with a few points for thought and time for questions. Sorry, imagine that you have a group of friends like this nice set here. And in addition to the fact that you know that they talk to each other, you also know the means of communication, right? So you know that, let's say, these two friends Snapchat each other versus these two friends only text each other. And so that is sort of a different view of the social network that is underlying this particular graph. And this can tell us a lot of things, right? So this can tell us, for example, the nature of the relationship may be more intimate if two friends are, let's say, Snapchatting each other versus just calling on the phone. But also ultimately, if, say, our goal is to detect communities, meaning sort of densely connected subgraphs in that graph, then ideally having more data should help us do a better job, right? And so those communities will be hopefully more accurate if we're able to sort of use the additional information that we have in such a way that we extract those communities better. And those communities will also have some context, meaning that, hey, all those people are really close friends to each other versus maybe all those people are maybe work friends and they only occasionally correspond with each other. And so that is an example of a multi-view social network or a multi-view graph. And now being the linear algebra enthusiast that I am, and many in the audience perhaps would do the same thing, the first thing one does when they get a graph is to create a adjacency matrix where here, you know, you can have a binary matrix where just you denote whether there is a presence or absence of an edge, or you can have more sophisticated things like a weight corresponding to the number of times, let's say, those people communicated. And now bringing this into the ball game of matrices is excellent, because now we can use a large toolbox that is afforded to us to do a lot of great things. And one of them is to analyze this adjacency matrix and to analyze it into sort of rank one factors in particular. So for instance, let's say that we have this trivial example of, let's say, all those different people up here being connected to each other and all those people down here being connected to each other. Then if we do a rank 2 decomposition, then we can just basically tease out those two communities. And not only that, but also identify memberships of those people to communities by just looking at the high values here, non-trivially, the non-zero values in each one of those factors. And that's great, right? And there's a lot of fantastic work that spans decades in how we can do this, you know, going all the way from the SVD to non-negative matrix factorization to more sophisticated things. But this is not what I'm going to talk about, because what happens is, well, this is great, but what's going on with the rest of the views, right? So Do I do each view separately and then somehow combine and hope for the best? Do I sort of combine the views, but then if I combine the views, then I'm kind of perhaps ignoring important data, ignoring important structure. And so if I want my cake and eat it too, then basically what I want to do is, perhaps at least my favorite option, is to model this data as a tensor, which for the intents of this and purposes of this talk is a multi-dimensional extension of a matrix that really beautifully can model what we call multi-aspect or multi-view data. In this case, each frontal slice of the tensor is an adjacency matrix. If we stack them together, then we have a 3-mode tensor. And the reason why, and my love for tensors goes back to my time in Hanya, as Xiao very correctly pointed out. My fascination, though, also stems from the fact that these methodologies have been actually applied and sort of been useful, tremendously useful, to a very vast and diverse array of applications, starting from psychometrics to chemometrics to signal processing, and then lately to machine learning and data mining. And the fact that all those different fields have been discovering that those tools are very useful and making contributions to those tools in the process, to me, is a fascinating thing that perhaps captures some universality in the utility of those tools, and that fascinates me. Now, a shameless plug is that actually, with a lot of great friends, including Xiao and perhaps more in the audience, but I cannot see the participants right now, we have put out here on the left, there's a transaction signal processing paper that gives you everything you need in order to start tensor research. Of course, you need to read it with, let's say, a cup of coffee or your favorite poison, but this is everything you need in order to then start algorithmic research. And then on the right side, there's a sort of contemporaneous kind of survey that we put out that details different applications in data mining and data fusion, which is sort of from a practitioner's point of view, if you're kind of sold on the tensor idea and want to see if you can use it for your application, how would you go about it? But plug over. Now, what are we looking for given that tensor? Right? It's the same as before, where we had the work friends and the college friends in the matrix. Now we're looking for those dense blocks, but those blocks span the 3rd mode here as well. And so those blocks basically are effectively what we call co-clusters, which is sort of a clusters that give us a subset of the users who maybe, let's say, they are the senders, a subset of the receivers, and a subset of the means of communication. And you can also see this as a contextual community where you have a group of tightly connected users and a subset of the means of communication under which this community is sort of exhibited, right? And so this is what we're looking for. And this may not come as a big surprise to many of the audience members, but the great news is that the rank 1 sort of notion that I just used to decompose that rank 2 matrix before extends beautifully and directly to the tensor case, where now you have a 3-mode tensor, then we just need the 3rd vector in order to sort of express that rank 1 block. And the more dimensions, or rather the more modes we have, the more vectors we need. But this is great because now we have the mathematical tools to express what we really want, which is, how do I extract those blocks from the data? And how do I do that? Well, again, my personal favorite way is the CP or canonical or perfect decomposition, which basically is the decomposition of the data tensor into R rank 1 tensors, each one of them being this triplet of vectors. And then, basically, we would write the tensor as this low rank part plus some potentially high rank noise. And this low rank part is just parameterized as this perfect decomposition, where basically each one of those, this is denoting the rank 1, sorry, the outer product. Each one of those vectors is one of those triplets of vectors. And if we take, let's say, all the A vectors and put them all together, then they form a matrix A whose columns are those vectors, and so on and so forth for B and C, right? So this is how we're going to represent this sometimes, and this is what it means. And in the context of our application, what does it really mean? Why do we like the decomposition? Is not just because it can easily extract those blocks, but because it has an intuitive interpretation. And so if this is a user by means of communication tensor, then there's two ways of viewing those factors. One is each one of those triplets, each one of those, as we affectionately call it, chicken feet, is, and I'm sorry, it's close to dinner time. If you are in the mood for dim sum, I apologize. But each one of those triplets of vectors is basically going to give me effectively a co-clustering of users, and means of communication, where I just look at the high values or the non-zero values, and as Xiao alluded to, one of my earliest works is basically on how do we add sparsity constraints here to make sure that this is in fact a really accurate co-clustering. And so this is one interpretation. The other one is, if I focus on Mr. Cartman here, and I just take the row of the A matrix that corresponds to Mr. Cartman, then that is what kids these days would call an embedding to the community space. If we believe that there are R communities in this graph, then this is basically Cartman's sort of embedding or Cartman's participation into each one of the communities, especially if we sort of insist on having non-negativity constraints, which would give us a participation and not negative values that we cannot really interpret here, right? And so this is great because we can actually use this decomposition to do community detection, meaning that for each one of those folks, we can use this embedding here to try to see which community they belong to. And this is exactly what we did back in 2013. This is kind of an earlier work, but this was the first one to look into the problem of community detection, unsupervised community detection, using the pair effect decomposition. And here, we don't have a social network, we have an academic network. So we have data from a DBLP website, kind of like a Google Scholar, but for the computer science sort of subgenres of research. And so the nodes are people, researchers, and the communities are hand-labeled research communities within computer science. And here, the view here is who cites whom. So people who cite each other are presumably working on similar stuff. Here's who co-authors papers with whom. So again, people who co-author papers together are presumably working on similar areas. And this is who has similar terms, same terms in their titles and abstracts. And again, the same kind of notion. And this gives us different views on how different authors may be connected to each other in terms of research field. And our job is to, for each author, identify which community they belong to. So what we do is a very simple thing. We just take the pair effect decomposition, and then we take the A matrix, we take each row corresponding to each researcher, and we take the argmax of that, meaning that we just take the maximum value. Here, if we have 3 communities, then the maximum would be community number 2. And this is our labeling for this person here. Now, one may ask, well, what if you choose matrix B? Typically, we get similar or the same result or very similar result. But we would like to have this flexibility in case we have sort of not symmetric matrices that we would like to express that with a matrix B. And this turned out to outperform actually any 2-dimensional baseline, meaning any clever way in which I would compact or combine the different views in a single matrix, and then do spectral graph clustering on that matrix. And so this method outperformed in terms of NMI, normalized mutual information, which measures the agreement of the labels for communities that our algorithm gives versus the ground truth labels, right? And so this was sort of exhibit A. And this obviously, since then, there's been a lot of great work by many folks that has superseded this particular work, but this was the first to show that this is actually doable, and this can be done also in an unsupervised way. All right. Now, one thing I want to sort of talk about is how do we bring now those tensors? How do they fare against those modern node embeddings, right? Because I called this thing an embedding, and maybe that's a linguistic stretch, but how do those things fare against, modern neural network-based embeddings. And for that, we need to take a slight detour just to remind all of us of the word-to-vec word embedding, which is what started it all, which is a really sort of clever idea that basically uses a neural network to try to predict, given a word, try to predict its context, right? The surrounding words. And this has given us a lot of great examples where, in the nearest neighbor space of, the vector that is king minus man plus woman is the vector for queen. The nearest neighbor space of the president minus power is prime minister, and cool examples like that. But the cooler thing is that, in fact, we don't need this skipgram neural network to compute word-to-vec. In fact, if we take a matrix where on the rows, let's say we have the words which we want to embed, and on the columns we have the context terms that we are using to measure the contextual similarities across words, and we take the point-wise mutual information of the two on the entries, and we factorize this matrix, we actually get exactly word-to-vec. And so that's great. And so that means that there is a connection between those neural network sort of skipgram neighborhood-based methods and factorization inherently, right? So not all hope is lost. Maybe our methods can fare well against things like that, right? So now moving on to node embeddings were inspired by word embeddings. And now instead of having the words around, what is the neighborhood of the node is basically defined by a random walk around the node. And then doing that, we identify the neighborhood of each node, we pass it, and then we do exactly the same thing, and we learn this embedding in that neural network fashion. And there's variants of that. Deep walk was the first one to do it. That was doing a uniform random walk. Node2vec was a subsequent work that was doing a biased random walk, and so on. And there's also work that incorporates features by embracing the factorization sort of definition of embeddings, not the neural network one. And so given all that, we wanted to see, especially in cases where we have a graph and we have node attributes, how can we define a tensor embedding that perhaps is competitive to things like this TADW work, for example, that was at least at the time the state of the art in incorporating side node features into a node embedding. And so what we did was, so it appeared at Asanam 2018 with a number of wonderful co-authors. And the idea is the following. So we have our, this Y is our original adjacency matrix, node by node, right? And then we have a node by some feature dimension T, which is a feature matrix. This could be demographic features, or this could be, let's say, textual features, so whatever they type and they send and so on, right? And what we do is given those feature vectors, we just generate a k-nearest neighbor graph, Z, that is again node by node. And what we do is we stack them one after the other. And now we have a tensor, right? This is, again, 2 slices in this trivial case, but we can have, we can add more slices if we want to add more different values for k, for the k nearest neighbor, and so on. And what we hope here is that those 2 different graphs capture sort of our different glimpses of the same underlying sort of node similarities that exist in reality. And if we take a CP decomposition, a pair-effect decomposition, this will give us the A and B matrices will give us, again, the node embeddings. And now we can directly compare them against Node2vec and Deep Walk and so on. And we actually do that. And turns out that doing that in a number of different standard benchmark data set, this actually outperforms the traditional node embeddings, which is not a big surprise because we are also using the feature information, but also outperforms the state of the art in doing modern day node embeddings using also side information. And that was a very nice result to see that actually tensors are still alive and well in this, in this brave new world of neural-based sort of graph embeddings. And so that was a nice thing to see. By the way, if there are any questions, please type them on the chat and Xiao can relay them to me. You can do that at any time, and please feel free to interrupt me by doing that. Now, one thing I want to sort of talk about, and for a moment contradict myself, is the fact that hopefully I convinced you that, those blocks is what we really need to find, and this is all we need in order to identify communities. But in fact, this notion, however nice and kind of like really fortuitous in terms of the decomposition that we can use to identify it, can actually be very restrictive, right? And so this rank 1 tensor, which translates into a block, if we sort of put it into graph terms, this is basically a full click between all those nodes, right? So it kind of captures the fact that all those nodes are really, really tightly connected to each other, and more likely than not, they're all connected to each other, right? And so in some sense, this can see full clicks, and sometimes even if a full click is not there, it may actually promote seeing a full click, because that is the best thing to do in terms of reconstruction error and the model that we've chosen. However, this may not be always the case when we have rich structure in our graph. And so 2 examples I want to raise. One is in a knowledge graph where, let's say, we record facts like Trump is president of the US for a little while longer, Merkel is chancellor of Germany, and Mitsotakis is prime minister of Greece. Now, this, if we fit a CP decomposition there, Trump, Merkel, and Mitsotakis will be in the same triplet as his president, his chancellor, and his prime minister, and then USA, Germany, and Greece will be also on the third mode. And if we were to try to do some inference of unknown facts, we may be tempted to infer that Trump is chancellor of Greece, and that is something that does not really compile, right? And so there is this block structure doesn't necessarily carry over in that particular case. Or let's say that we have a social graph. If we have a social media Instagram influencer that tons of people follow, but they don't follow nobody. Or let's say we have a spammer or a telemarketer that if we were to observe their connections in a phone network, then they would appear as a star graph where they're in the center, and then they just have a bunch of satellite connections because they initiate all those connections, right? And so there's a lot of rich structure out there, and if we are looking for blocks, then we may miss the structure, right? And so this is work that we just recently presented with my student Ekta at WWW, or rather the web conference as it's called these days, where basically we seek to identify also the structure of the community. And this was inspired by earlier work by Denai Kutra and others, where the idea was you have a large graph and you don't really know what's going on in there, but if you use a finite small sort of alphabet of different graph structures, let's say a click or a star graph or a chain graph, then how can you encode the entire, this beast of a graph into a small number of those elementary graphs, right? And so that's, they do that through minimum description language. And they actually find really interesting patterns, for example, in the Wikipedia sort of co-editing graph, where you can see people going and fighting against each other when they edit a particularly controversial entry in the Wikipedia, right? But then our interest is how can we extract that structure automatically? How can we let the data tell us what is the real structure in the community? And what we need to do is we need to kind of like expand a little bit our definition of what a community is in the tensor. And what we need to do is we need to have more expressivity in the 2 modes that refer to the graph dimensions, right? So A and B are the 2 graph modes. And here, because they are rank 1, they can only model this block. So if we sort of beef them up a little bit, then we can actually, if we say that those have to now be rank L blocks, not rank 1 blocks, then if we, let's say, multiply those A1 and B1 out, then that's going to be a rank L matrix, right? That is going to be able to capture the adjacency matrix of a more complex elementary graph. And that would now be the shape of the community that we would like to discover. And so this has a name, and it's a simple sort of version of the block term decomposition. It's the LL1 block term decomposition because it breaks down the tensor into terms that are of rank L, and rank 1. And this is what would conceptually look like, this community would be a star, this community would be a near clique, and so on. And so we give the decomposition enough bandwidth to, so to speak, to be able to represent richer structures in the data. And so this is what we did. And one thing I want to show you here that, from the multitude of results in the paper is how successful that is in when we know for a fact that we have planted, special structures, that in fact this richness in the L, the dimensionality of each one of those blocks is actually helpful for recovering those structures. So here we plant cliques and stars in a graph, and we model it using the L11 decomposition, and you see that there is sort of, after a certain point of the L, the block rank L, we're able to discover all the structures that we've planted. And so that speaks to the expressivity of the cell. Of course, this is not by no means over, right? So sometimes we may need smaller L, sometimes larger L. How do we flexibly do that? This is a question that we're actively working on. But this is sort of the beginning of sort of being able to discover not just who is a member in the community, but also what does the community look like? Because that could also be a very useful piece of information to whomever is analyzing that community. All right. Now I'm going to switch gears. So it's a good time to ask questions if you have any at this point. And if not, I'm going to plow through Route 66, as you can see here. And I'm going to talk about sort of time. And I'm going to tease out time. I'm using time separately here because it's an interesting notion. But time can be another aspect, another view. Because let's say we record the interactions, or let's say folks publishing at conferences over time. That can be, different snapshots of that graph could be sort of an adjacency matrix that now can be formed to a tensor. And this now, can help us understand, the birth and then the death of different communities, or we can try to detect anomalies and over time, and then see how we can correlate them to real life events. And there's a lot of work on that that sort of uses time as this extra sort of view in the graph. And that's sort of an example that, again, goes back to the earlier work we did back in Chania, where we were looking at the Enron employee graph, the employee by time. And here you see we have somehow encoded a labeling of the community. Let's say this is the community that is mostly senior legal folks. This is another legal department subset, and so on. And we also see for each one of those departments or communities what is the temporal evolution of how frequently they communicate in the graph. And you can see interesting things that sort of different interesting spikes that align with when the SEC investigation began and when sort of the CEO started to change and so on. And you can see, all those things that are now public record, and Enron is probably one of the most well-studied data set of the sort because of that. But you can sort of see all those interesting events unraveling in front of you just by doing this decomposition, right? And so time can be a really useful mode in a tensor, but this can also be, time can also be sort of in the real sense of time. Your tensor can also be growing as time passes. And so if you have a temporal graph, a time-evolving graph, let's say, in your Facebook or a major sort of company that records graphs like that, then literally every second you have a meaningful, new set of interactions that arrive as a slice in your tensor. And if you were into this whole tensor decomposition thing, then how would you incrementally update the decomposition in order to account for new data, right? So that's the streaming tensor scenario and the tracking the decomposition and so on. And of course, there is a lot of great earlier work by Dimitri Nion and Nikos Sidiropoulos, and then there's also by George Yanakis' group and so on. And there is a lot of work in trying to sort of track the decomposition, but at least sort of the state of the art of it, which was 4 years ago, is able to do that, but it's not able to scale up to very large data because it models the entire ambient dimension of the tensor, also not taking into account sparse data. And so what we, and I'm not going to go into detail, but what we tried to do in the last couple of years was to try to express this incremental tracking of the decomposition by using some form of sketching, some form of summarization of the data and the incoming updates, so that everything is done in sketch space. And so things are staying really, really efficient and approximately sort of performing as well, sometimes a little bit less so, but usually on par with the exact methods. And so those are sort of two of the works. One of them appeared at STM 2018, and the other one appeared at CAMSUP 2019. And then one of them has to do with randomized sampling of indices. The other one has to do with randomized compression, right? But both of them sort of try to save time and space in doing the updating of the model given the new data. Now, where I want to get to, though, is the following point, which is that virtually all the work that I've seen, and I apologize if I have missed any that does not make this assumption, but virtually all the work that I've seen, including our work, by the way, right? So I'm not taking us out of it, is basically assuming that the rank, as we're tracking this thing, the rank, the number of components stays the same, right? And so that is an assumption that maybe in some cases is a fair assumption to make if we're not expecting a lot of variability in what's going on. But this is perhaps not always an assumption that captures exactly what happens in the data. And so this is a paper by Ravdeep and Nekta that appeared at ECML PKDD in 2018. And there, what we do is we sort of start the discussion about this idea of the rank changing and sort of new concepts appearing or disappearing as the data is coming as a stream. And so the paper also, we sort of define how what we mean by this concept drift. And we also have a sort of simple algorithm that detects it. And the algorithm is called seek and destroy. And this is because Ravdeep, my student, and I have a bet that each one of his papers will have a method that is named after a Metallica song. And so this was, I think, his first paper. So that was, and we're moving on from there. But seek and destroy basically is a very simple algorithm. And what it does is at every step where we have to merge a new batch of data, it estimates its rank. And it's a big sort of if around it, because that is done using current state-of-the-art heuristics, which are actually, unfortunately, not perfect. And so, but we're doing our best to have a good estimate of that. And so what happens is if we detect, even if we detect the same rank, we detect a matching between components. And if there is no matching, or if some components don't match, then that means that perhaps there's a new component that has appeared. Let's say a new community that has come into view. And this way we augment the column space of the factors in such a way that it accommodates this community. I'm not sure if there's a chat. Let me see what.
No, that is actually just a long question for me. I can actually ask it later on.
Okay. Thanks. Because I have host privileges, so I can see that. But maybe we can talk about it after I'm done with the main part. Thank you. So what I'm going to show you is how do we evaluate that thing? Well, that's a toughie because we don't really, know, for a fact that in this data set, in this real data set, there is concept drift, and here's how it happened, and so on. At least there are data sets that are meant to measure concept drift in supervised learning, but not necessarily not in this scenario here, right? And so what we do is, first line of defense is we need to create synthetic data where we simulate that in such a way that we know that we can capture it. And what we do here is we create synthetic tensors that we sort of stream over batches, and we kind of like see the rank increases as we get every new batch. So we start with rank 2, and we finished in rank 5 or rank 10, depending on different experiment. And here we see that we can actually at least capture pretty accurately the fact that the rank changed. So that's good. Furthermore, we want to see, okay, we do that. Does it help in any way, right? Or is this just an academic curiosity that doesn't mean anything? And so what we need to do is we need to compare, let's say, how well we're approximating the data, given that we are discovering this concept drift versus not. And what we do is we compare against online CP and Sambaten. Sambaten is the randomized index sampling method that I showed you from STM 2018. And we have two different universes. Universe number one is the realistic universe, where the final rank or the full rank of the data, if we had all the data in front of us, is not known. And so what we give to every decomposition, every method, is the initial rank of the first batch, right? And in this case, it can destroy beats the other methods. In the unrealistic universe, we give a little hint to the non-concept drift detecting methods, which is, this is the entire rank of the entire data, and they start with using that. And this sometimes turns out that they actually perform as well. And so, but this is an unrealistic scenario, and we don't really also check the goodness of the components themselves, which is what we ultimately care about here, right? But the reconstruction error seems to, in the end, be sort of unscathed in this unrealistic scenario. Now, in real data, we have some evidence of that drift if we stream that data, and that is, if we stream the end-run data set, then we actually see that Seek and Destroy can get a better reconstruction error by sort of doing its thing and discovering coming and going concepts compared to sort of the other streaming methods. And so that's evidence, but not conclusive proof of that drift. But this is, again, another thing that we are really passionately looking into and trying to extend in different ways. The last chapter, which will be hopefully not as long, has to do with adversarial machine learning. And perhaps this image everybody has seen. I know that two of our organizers spent a lot of time in Chengdu, where those adorable beings are sort of, is their hometown. I'm given to understand. And so what happens here is that if you have a picture that looks like this panda, and you somehow perturb it in a way that is very targeted, in a way that you basically get the gradient of another example from your neural network and add it to this example with very much, like, very, very small amplitude, then that now sort of bumps that example to a different part of the boundary, and then it's misclassified, right? Another sort of more terrifying example is that you can actually mess with the visual recognition of traffic signals by sort of adding different stickers on stop signs and such. And this is, this is an academic paper here, but earlier this year, in February, it was reported that basically folks were able to trick a Tesla into speeding more than the limit by sort of taping, I think on a 25 miles per hour thing to make it go 50 miles per hour. And that's not, just an academic curiosity, but it can actually have real implications in real life. And it is a very, very interesting problem to try to understand how those otherwise really accurate and sort of scarily high-performing convolutional neural nets, for instance, are able to just be so easily fooled, whereas a mere mortal like myself is able to totally tell that this is a stop sign, right? And so how do we even go about this? Well, there's a number of ways that folks have tried to address this problem. What we are not going to do is what people call adversarial training, which is you also show some examples, adversarial examples to the network, and that way the network kind of knows them and doesn't get fooled by them. But we're not concerned with that. We're concerned with, we don't have access to the network, we only have access to the examples. And if that is the case, then what we can aspire to do is to somehow clean the example, right? So let's say that after this perturbation, the classification of X is not the same as of X prime, but they were very, very similar, at least in terms of some norm. And what we want to do is we want to apply some preprocessing so that the classification of that post-processing rather is the same as the original class, right? So we want to bring the data point to the same class by applying this transformation that hopefully, I mean, not hopefully, we should clean the data, but also not perturb the data to the point that it destroys the structure in the data. Now, what I'm going to do is I'm going to, instead of show you results in images, for now, I'm going to show you results in graphs and attacks on graph convolution networks for now, because the theme was graphs, and then we're going to go into the beyond and look at images. But for now, this is a nice, a very famous attack, the NETAC, by folks from Technical University of Munich at KDD 2018 that actually won the Best Paper Award that year. And the idea is, how can you fool a GCN, a graph convolutional network, by making perturbations in edges and node attributes, and in such a way that those are undetected in terms of the distribution, let's say the degree distribution of the graph, but are targeted in misclassifying the node. And again, this is not a curiosity. You can basically see this as buying fake reviewers or fake followers, introducing new nodes to your new edges to your edge, new edges to your node, so that you fool the classification of your node to something else, right? And so this perturbation is very interesting in many ways, but the most interesting way that we discovered is that this perturbation actually appears in a very high rank part of the spectrum, right? So if we take, let's say we take the SVD of this graph, not even a tensor decomposition, and we look at the where in the singular value do the perturbed graph and the real graph differ, that will be really along the way of very high ranks. And so as the title says, all you need is a low rank to basically clean up the attack. And so here I'm showing that basically taking a low rank approximation of the graph itself using just the SVD here is able to restore the accuracy. This is basically the number of points that are above this line here means that they're correctly classified. The number of points under here are incorrectly classified. And so here you see the attack is basically just making all the points to be really incorrectly classified. But then as we sort of do a low rank approximation, we're able to restore most of those points to their original space, which is here's what would happen without the attack. Here's after we do the approximation. And also, if we, instead of a GCN, we use this T-Pine, the method of the node embeddings using tensors that I showed you, we can actually also have really, really robust results that are not affected by this kind of attack. And this is a paper with my student again that appeared earlier this February at Wisdom in Houston, at a time that we could still travel. So that's missed that time. But now let me just very quickly talk about images. And this is a really nice observation by folks at Georgia Tech, where they observed that actually the perturbation is also of high frequency. So what they do is they do a JPEG compression, randomized per block, so that, because randomization is really good when we're talking about defenses against attacks. And this JPEG compression results in actually removing that targeted noise that would otherwise misclassify this adorable Labrador, and restores the accuracy. And so if this perturbation is high rank, then perhaps it might also be, high frequency, then it might also be of high rank. And so what we do is, in this recent work with McGinn, we're looking into how we can bring the graph defenses into images. And in fact, a low rank tensor decomposition does the trick much better than the JPEG compression. And here, I'm not gonna go through the list, just the different options of what decomposition we can use, but TensorTrain here appears to be a better choice because we're dealing with RGB channels and a high order tensor. But what happens is here we have the different variations of tensor up here, and SLQ is the Georgia Tech method, the JPEG compression method. This is the runtime for the entire batch, right? So not a single image, but a big batch of images that are perturbed. And you see here that the tensor methods are about as fast, maybe a little bit slower, but are much better at restoring the accuracy of perturbed images. And that's another really nice thing that we're able to kind of like see transcends different problems in deep learning and attacks in deep learning, right? So there's some kind of universality in this low rank approximation of the input data that helps alleviate those problems. And with that, I would just like a few points for conclusion, right? So I have this condition that I see tensors everywhere, and you know, they might be there, but they might not, but that's who I am. But it's a fascinating area that has a lot of open problems still. And one of them is sort of especially pertaining to the exploratory and supervised analysis, where there's a lot of challenges in understanding how you would, let's say, take data from someone in a different domain and understand what kind of, from the whole zoo of tensor decompositions that may be useful, what kind of model should I use? How many useful patterns are there? What is the structures that I should be looking for? How am I not fooling myself, right? And these are questions that even though people have been thinking about them for years and decades, they're not answered to this day. And I'm not aspiring to answer them all, but I'm really challenged and motivated by sort of trying to push the envelope there. And the other one that I'm really excited about is where do these tensors fit in this brave new world of deep learning, right? And so, for instance, we can see here that we can actually successfully defend against adversarial attacks by those really nice, simple linear or multilinear rather models, right? Are there any instances in which tensors and deep learning are a fortuitous couple, right? So this is another really exciting future direction that I think has a lot of potential. And with that, I would like to thank you all for your attention and thank the organizers again for having me here and giving me the honor of talking to you for 45 to 50 minutes. And I'd like to thank my students for all the hard work and all the sponsors who have sponsored the work. The coffee we bought ourselves. So, you know, this is a rank 1 coffee that is a lab thing. And with that, I'd like to welcome all your questions at this point. Thank you.
Okay, right. Thank you very much, Vagelis. A lot of fascinating things. Any questions? I saw To has a question, a very long question here. To, would you go ahead and ask your question?
Yeah, sure. Okay, so I mean, first of all, thanks, Vagelis, for the very nice talk. So actually, I have some question about the first work that you presented about the clustering of the nodes. So so I'm trying to, first of all, trying to understand the model behind this this idea of clustering like an array of network or an array of graphs. So is it like that you're using? Is it right to model that those graphs that you observe at different layers are in fact like a noisy observations of the same ground truth? Am I right to interpret
yeah,
this?
This is a very good way of putting it, actually. Yeah, and if that is the case, then you get to see the benefits of modeling them as a tensor. If you have graphs that are uncorrelated with the ground truth and kind of like uncorrelated with each other, then, you know, garbage in, garbage out, right? But if what you're saying happens, then yes.
Yeah, because the reason why I want to ask that is I want to know what would be your take on something like multi-layer graphs. So things like maybe like, for example, like in the transportation networks, so you have the same node at different layers, at different layers of the tensor, but they do have really different edges because, you know, like, for example, you can perhaps like take an Amtrak from Los Angeles to San Francisco, but you cannot take an Amtrak to Phoenix, for instance. But then you can fly to Phoenix and you can fly everywhere.
Yeah.
So, I mean,
that's a great,
like,
yeah. That's a great observation. And you know, against all my best nature of saying that tensors are best for everything, maybe tensors are not suitable for this kind of formulation, right? So there is, like, for example, I'm not sure if you know Han Tong, the UIUC now. He was at Arizona State, and he's doing a lot of work in these networks of networks kinds of
Yeah. Oh, okay.
distribution, and that, you know,
Oh, yeah.
and so you know, I would say I would urge you to look at that kind of work, and perhaps other ways of projecting this data. Maybe not a factorization, but let's say some kind of CCA. Like Xiao has done a lot of great work on that. For example, could be a way to go here when the feature spaces are so heterogeneous that you know we don't have that you know correlation in that ambient space, right?
Yeah, I see. Thanks.
Right. Thank you.
I do have several questions, but I'll hold my questions and give the opportunity to audience. Any questions in the audience? You could also unmute yourself and ask. Okay, if you don't have a question, then I'll take the opportunity. So Vagelis, I like the idea of using LL1 to do the to basically extend the co-clustering idea. So I know what you did. One of the motivation is that you said in KB, in knowledge graph, in knowledge base, you want to use some more structures, right? Did you try this on any knowledge graph?
Yeah, we actually tried it on the WebKB knowledge graph, and I mean, we tried it in terms of discovering useful structures. I don't remember now if we tried it also in terms of completion, but then my interest is less on completion and more on accurate representation of the structures themselves. Because if we're gonna if we opt for completion, maybe like a Rescal model, like a Docker 2 model, basically, may be better because it captures more complexity there. But if I'm not mistaken, we definitely tried it on a number of knowledge graphs.
Okay, so was it in the paper or?
It is in the paper, yeah. It's just that
you didn't run it on prediction or completion tasks.
No. The paper is exploratory. The point of the paper is exploratory analysis, right? I'm not sure if that would be giving the best results in completion, but it might give better results than Parafact. But that's not to say that this is the best we could do for completion, if that makes sense.
Okay, yeah, that's fair. That's fair. But because I've been thinking about which model is better for completion tasks, and thank you. Another question that I had is the adversarial attack part is fascinating. So I think the low rank observation is very interesting. So I wanted to ask you, what's the major insight behind this? My guess is that because these perturbations are highly is very carefully designed, so they could not they are not a universal noise, isometrical noise, so they couldn't be everywhere. And right. Because they have a very small energies, so it makes sense to assume that they are in some small subspace, right?
That's exactly right. That's exactly right. And we actually also, there are some theoretical results that we became aware of after we postulated the observation that talk a little bit about if you basically kind of like if you perturb a graph in such a way, what's going to happen to a particular singular value of that graph. And we can actually now bound the, we can give you where to cut. Basically, in the paper, we have all the details on where to cut in order to be sure that you're sort of not cutting useful information, but you're exterminating the perturbations.
Yeah. Okay, that's a very nice. I think I didn't know this before. That's a very nice observation. Thank you for for giving us this information. A follow-up question is that why tensor train? Do you have any idea why tensor train works better for this particular problem?
Well, so I think it has to do with the fact that because we are now talking about an RGB tensor of a bunch of images, so we have a higher order tensor. It is, it was faster and marginally better, right? But it was mostly the speed that we wanted. It's a two variable optimization problem here, right? So both the speed and the restoration of accuracy, right? So all low rank decompositions worked very, very well, and all of them better than the JPEG compression. But TensorTrain, because of the fact that it's a very simple sort of series of SVDs, right? So that's why it was the winner in terms of the speed. Yeah, of the whole batch of images.
Did you observe SVD, just plain vanilla SVD? Does it work?
It does, but not as well. And the assumption there is that if we batch multiple images, there is structure to be learned there of what natural images look like, right? And so that's kind of like that's reasonable to assume that the perturbations being high rank and everything would be somewhere else, and then the subspace of natural images also is reinforced by just adding more natural images and not doing each one in isolation. But even doing a simple SVD does work, but it doesn't do as well as doing the batching in tensors.
All right, thank you for for your answers. Okay, so any other questions from the audience? Perhaps for the sake of time, we could take another question.
If there are no questions, or in the meantime, I can also do a public service announcement that says this is a cortado, which is not a latte, but it's a smaller piece of coffee. And it's to me, the optimal ratio of espresso and milk. So now you know that.
Okay, so if there's no question, let's wrap it up and call it a day. Just a reminder: next week is a holiday week in the United States, so we will not be having a seminar. So our next seminar is December the 3rd. So the week after our Yuyotan, our next speaker will be Professor Nikos Sidiropoulos. He will be talking about a nice connection between tensor decomposition and the joint probability estimation and its applications in machine learning. So, so we will be sending you reminders, and the YouTube video of today's talk will be uploaded very soon. So if you want to come back and check out today's talk, you can also come to our website to get the YouTube link. Okay, thank you all. Thank you for being here, and I look forward